Hello. Hi, this is Debomitra Dey, and I'm a food extrusion specialist with CW Brabender Instruments at New Jersey, USA. Firstly, I would like to take this opportunity to thank the organizers and for inviting me to present on the application of FTIR in food sciences. So the topic for the invited talk is qualitative measurement of food extrusion phase process-induced changes using FTIR spectroscopy. So to begin with, I'll be giving you a brief overview of my presentation. So firstly, I'll like to talk about what extrusion processing is, and then I'll quickly move into the introduction of FTIR. I would not take a lot of time talking about FTIR, about the principles and the introduction, but the main focus of my talk would be more on how food scientists are trying to use FTIR, especially when it comes to understanding the process-induced changes during extrusion. And I'll be discussing on 3 different studies that have picked up who used FTIR to understand the process-induced changes during extrusion processing, and how these researchers tried to correlate the final product characteristics with what exactly is happening on the chemical scale using the aid of FTIR spectroscopy. So to begin with, what extrusion processing is. So here, the picture that you see on the slide is the twin screw extruder called the Twin Lab F. This is manufactured by Brabender, the company where I work for. And now moving on to what extrusion processing is. So extrusion is basically the science where you're trying to push a material you're firstly processing the ingredient inside a closed barrel, and then trying to push that material out through a designed opening. So while we say designed opening, so the die and the material through which the process ingredient comes out through is called a die. And this die could be of any design. It could be circular, it could be square, it could be a triangle, it could be anything. It could be a star, anything of that sort. So that's the reason I call it as designed opening. So the extruder is an extremely versatile equipment, and it can handle a range of products. So for example, in this case, if we are just talking about food, so it can handle ingredients like starches, proteins, and fibers. And we can also make any kind of product that you want to make out of the extruder. And the best part about extrusion processing is that it's a environmental friendly process. It's a low cost processing technology, and at the same time, the machine is extremely versatile. And because of this versatility, extrusion has found application in a number of industries, right from rubbers, plastics, and polymers, even in the food industry. So extrusion processing was, or maybe I would say that it was introduced in the food industry in the early 1900s. And since the beginning, it has been used for processing a lot of products like breakfast cereals, pastas, and noodles. And now we see a lot more application of this processing technology. So this is the range of extruded products that I was just talking about in the earlier slide, that we can have a die with different designs. And this is a result of having a versatile equipment or a machine that gives you the freedom to make any kind of products that you want to. So there are these bulk products, for example, Cheetos that can be produced using the extrusion processing. Similarly, this is the image of a plant-based meat product. This is also made using an extruder. Similarly, this is the puff product that I just mentioned. And then we can have products with different sizes and shapes, different colors. You can just put in anything inside the extruder, and what you get outside is a product that you desire based on what kind of raw materials you're adding it into, or what kind of materials you're feeding into the extruder. So now, since we got an overview of what extrusion processing is, now let's quickly look onto what really happens inside the machine. What I just spoke to you was a broad overview, like a zoomed out vision of what's happening. Now let's try to zoom into the machine and see what really is happening inside when we put the material, or how it is being processed, and why the material comes out like this. What's the reason for that? So let's move on to the next slide. So this is just a view inside the extruder. So I'm going to walk you through what really happens inside the extruder. So firstly, one thing that we can see here is that we can see the screw. So this is a representation of a twin screw extruder, which means it has two screws for processing the material. The reason for having two screws is that two screws give more amount of shear, more amount of uniformity to the product when the product is processed. And it of course gives you more flexibility in handling a range of raw materials. So in this example, what we are trying to extrude is a preconditioned cornstarch. So preconditioned meaning that it has already been some amount of water was added to cornstarch and kept overnight, and then that particular material is being fed inside the extruder. You have another option where you can just have the raw material and you can dose in water through one of the sections here on the extruder. It depends on what exactly you're looking at or what your desirability is when it comes to the product. So right now here we see that the extruder is divided into three zones. It's called the feeding zone, the compression zone, and this zone is called the metering zone. I have just divided these two zones just for the sake of what the phase changes goes through. So the first phase change that we see here, not specifically a phase change because here the material is just fed into the extruder. So here these are the screw elements which conveys the material downstream to the end of the extruder. And then when we see here, this is the compression zone. So here usually the screw diameters become smaller and then they try to compress the flour material. And then it is pushed to the metering zone where the material is converted into a rubbery dough. As you can recall that we already have water added to this particular mixture. So that's the reason when you are putting more force, it's very similar to the act when we are trying to make a dough at home. So when we add some amount of water and some amount of flour, and then you try with the kneading action, you see that your flowy raw material is converted into a rubbery dough. Similar is the thing that happens here inside the extruder as well. But the only difference is that inside the extruder, it is under high pressure, high temperature, and high shear. So that's what makes the difference while you do it by your hand and while the extruder does that job. And then as we go further downstream, again, the pressure and shear increases. And finally, this dough is converted into a viscoelastic starch melt. And finally, the starch melt is then being pushed out through the extruder through a small closed opening called the die. And this is what the result is, that the product expands when it leaves, and the product expands because the vapor and the heat goes out, or there's supersaturation or evaporation of water that happens, and that causes the expulsion of the material when it comes out through the die, and that causes expansion. So one thing to note here is that in the case of starches, starches have the ability to expand because of their ability to get stretched when they are pushed out under high pressure. However, in case of proteins, proteins might expand to a certain extent, but not as much as starch. So that's the reason, if you notice, a product like Cheetos, it expands really well. But as you try to add in other material, the expansion reduces because you're diluting the amount of starch. And these products are kind of inhibiting starch from from the action of stretching and being elastic. So that is one reason here that we see that these products might not have good amount of expansion. The reason why I'm mentioning this here is you will understand when we talk about the studies that are just coming up in a few moments. So once now we understand what extrusion processing is, what really goes inside. So now what we are trying to do is, as food scientists, we are trying to find a particular technique that will help us to understand what really is happening during this process to the starch. So for example, here we were talking about starches. So with extrusion processing and FTIR, what we want to understand is that what are the chemical changes that starch is going through during this. Basically, the difference between this and this, what really is happening, that's what we want to understand on a chemical level, and how we can control certain amount of changes or how we can correlate that. Okay, for example, some products are expanding very high, but again, some products are not expanding very high. So what exactly is going on inside? We want to figure that out. So that's the very reason of understanding FTIR processing. Because the problem is with extrusion processing is that it's very difficult to draw out samples in between the process, because extrusion processing is a dynamic process. And as I mentioned that it's under high temperature, high shear, and high pressure. We cannot just open up the extruder and just collect samples. So the only thing that is left to us, the devices that we are left with is that, okay, we have this, let's figure out the changes. That's the reason we want to study the process-induced changes. So this brings me to what exactly FTIR is. I'll be just giving you a very short overview. I don't want to put in much time talking about FTIR because um, I assume that all of us are really well versed with FTIR and know what exactly it is. So the main principle of FTIR is that the covalent bonds in the molecules, they selectively absorb the IR radiation of specific wavelengths, and that changes the vibrational energy in the bond. And another thing is that different bonds and functional group absorb different frequencies based on their bond strength and atomic mass. So this is what differentiates a compound from another compound, that, okay, this compound will only absorb IR at this wavelength, but another compound will absorb IR at a different wavelength. So that's how I would understand that, okay, my sample has compound A and compound B, because A has a different frequency of, different frequency at which it absorbs IR, and B has a different frequency at which it absorbs IR. And another thing about FTIR is that, as I mentioned, that it detects functional groups in samples, and it also provides a fingerprint of the compounds, because every molecule has a unique spectra. So that's how, that is one useful thing that FTIR helps us with. So that is what we are trying to exploit when it comes to understanding the process-induced changes. So this is a typical FTIR spectra. When we look at, so the one that you see here in the bottom is the FTIR spectra of cornstarch, a raw cornstarch. That is just the cornstarch flour. And this one here that we see in red and blue is the FTIR spectra of cornstarch that has been extruded at two different screw speeds, meaning at two different shear rates. So one thing that we see here, so in case of starches, usually between 900 to 1200 wave number is the fingerprint region of starches. So fingerprint region meaning that we definitely see some starting differences of what exactly is happening in this particular compound. So here, if we look at it, definitely we see some changes compared to this, and another sample that was extruded compared to the raw material. Definitely we see some changes. Now, these are again the process-induced changes. So process-induced changes, what could be the process-induced changes in starches during extrusion processing? So one change is, of course, gelatinization, because during extrusion processing, the starch must have undergone gelatinization. The crystalline structure of starch is broken because it was processed under high temperature, high shear, and high pressure. That led to breakdown of starch. And another thing is that there will be more number of amorphous structures, because of course we have broken down the starches. There will be more amorphous structures. So these are the three things that we can definitely see in terms of starches when it comes to their processing changes. And another thing is that definitely there are some changes here in the OH bonding region, but however, we can't be very sure of what exactly is happening. I cannot really say that, okay, whether the number of hydrogen or the hydroxyl bonds are reducing or the hydroxyl bonds are increasing. There is no quantity, or I cannot quantify to that number that, okay, there was X number of hydroxyl groups at A instance, and there is Y number of hydroxyl groups as another instance. We cannot really quantify that as of now. So this is one thing when it comes to FTIR spectra that we try to understand. Now moving on to some of the peak assignments. So as I mentioned earlier, that the region from 3700 to 3200 wave number is the OH stretching vibration. From 3500 to 3200 is the bonded OH. And then these are the regions of the fingerprint regions of starches. For example, the region at 1047 wave number signifies the amount of order of crystalline structure. So it is very obvious when it comes to an extruded product, this would be low. But again, the 1022 wave number region, the amorphous structure would definitely be higher in an extruded product versus when you're looking at a raw material, because of course there you have more number of crystalline structure as compared to the amorphous structure. So what are the potential applications of FTIR in analyzing extruded products? So there have been some studies where researchers have tried to understand the protein conformational changes the interactions between protein and polysaccharides, similarly starch conformational changes, and the starch fiber interactions that happened or occurred during extrusion processing. Another brief example that I could give you is just giving some extra information on this. So Ftir has also been widely used when it comes to detecting adulterants in food products, because of course adulterants, you can definitely understand if you have a different Ftir spectra or a different absorptions in the IR region, you can definitely figure out that, okay, my food must have a X adulterant, which is also one good way where Ftir spectra is highly used in food sciences. But coming back to our focus on process-induced changes, so I'll be talking about 3 studies specifically which talk about the process-induced changes pre-extrusion, like basically the difference between pre-extrusion and post-extrusion, what's happening, and how these authors try to correlate the textural properties to what could happen on a chemical scale during extrusion processing. So we'll be talking about the first study. So in this particular study, the researchers try to understand the effect of apple fiber inclusion in cornstarch during extrusion processing. So here the authors used 2 different kinds of fiber. One was the normal apple fiber or the native apple fiber, and the other was the acid washed apple fiber. So in this case, of course, when you're acid washing a fiber, you're trying to get rid of a lot of soluble components, and also you are trying to solubilize your insoluble fiber. So that is a difference between the native fiber and the modified fiber. So definitely we would see some different interactions per se in this case. So what the authors actually did in this study was that they just considered a certain area or the fingerprint region from 900 to 1200 wave number. So if you look at here, so here what the authors are, so the one that you see in green, this is the Ftir spectra of the native flour or the mixture that was used for extrusion processing. So here we can see that it has a high crystallinity index, but as we try to process the fiber, we are seeing that the intensity of crystallinity is reducing. Why? That is because the material has gone through extrusion processing. And similarly here in this case, the authors mentioned that there were some there was a peak here at 1035 wave number, which could show the possibility between the interaction between lignin and cellulose. So this interaction was observed in native fiber inclusion, but however, with acid washed fiber, this interaction or possibly this peak was not observed. But again, this is not very evident. So the authors also could not possibly talk about it very surely. And similarly, what the authors tried to say here was that there are definitely process-induced changes, but it's very difficult to pinpoint each and every, as in what are the interactions between cellulose and lignin, or what interactions happen between hemicellulose and cellulose. So this was one thing that the authors talked about. And basically, there are some key takeaways from this particular study. So which would be that the authors mentioned that the increase in fiber content impacted on the final texture of the product, and the interaction between starch and fiber negatively impacted the final product and the corresponding process-induced changes during extrusion processing. And this brings us to the second study. So in the second study as well, the authors tried to study 50% amylose starches with different mixtures of cellulose. So in this study as well, what the authors talked about was that the authors mentioned that there were some definitely very similar to what we studied in the earlier, what we talked about in the earlier study. So here there are definitely some process-induced changes, which is of course because of the changes in starch that is happening, but they could not really talk about what changes or what impact the cellulose put it, or what impact was cellulose, how cellulose was impacting on the extrusion processing. And the key takeaway from this study again would be that the authors found no evidence of covalent bonding between starches and cellulose. And the authors also mentioned that cellulose interfered during reassociation of starches and impacted on the crystallinity of starches. So what meaning of reassociation of starches is that? So starches have the tendency of reassociating themselves, which is also called as a retrogradation of starches. So in this process, during cooling down of starches, the authors mentioned that the cellulose possibly impacted that particular process of starch realignment, and that's the reason the products had a lower amount of expansion, or the texture of the product was bad. And this is one thing that the authors found was supporting of why is the structure changing with increase in amount of cellulose. Similarly, we have another study where the authors studied the extrusion-induced changes in rice, oat flour, and olive maize extrudates. So in this case as well, the authors try to explain us that they saw some changes when it came to comparing the conformation of starches and also the protein polysaccharide interactions that could possibly happen during extrusion processing. And that also impacted on the final texture of the product. So this is what the authors also try to mention with the FTIR spectra, but again, there is no starking difference to what. So here you can see the A stands for the raw material and B is for the extruded material. Similarly, C is for the raw material and D is for the extruded material. So if you see, we are definitely seeing some changes here in this region, especially the fingerprint region, but definitely it's not extremely very much not very starking or not very significant to talk about or come to a very concrete conclusion. So the key takeaway from this study is that, again, the authors mentioned about the changes in the carbohydrate components and protein structure and the changes in the texture of the extruded products. So overall, what I would like to mention here is that definitely we can see process-induced changes, which is very obvious because there is some breakdown happening with the molecules in place. But however, it's very difficult to pinpoint each and every specific little changes. So that's the reason FTIR spectra cannot possibly help us to understand the changes, but it can definitely be used as a supplementary technique where we can try to use this in combination with either XRD or NMR to further our understanding on what exactly could happen in a particular region. And till now, most of these studies concentrated on the qualitative aspect of what could possibly happen with the use of FTIR in understanding the process-induced changes. But definitely, if we try to shift gears and try to understand the quantitative or use a quantitative approach to understand the changes that is happening so that we can quantify and then we can understand that, okay, if X and X parameters are used, then there will be like a Y amount of change. And then to achieve that, I would try to back engineer my process and then try to understand and get a product of that desirable quality. And similarly, yes, it is helpful in understanding the shift in peak and the peak intensity, but they are only used as good estimates. It's again an empirical technique at the end of the day. We do not get anything out of it completely. So I'll be open to suggestions, and if you have any inputs to give, it will be really great because that will help us to go a little further in understanding what exactly is happening, given that we cannot really open up the extruder and try to understand what really is happening. So I end my presentation here and thank you for your patient hearing. And again, please let me know if you have any questions. You can send your questions to me at my email ID, as you can contact the organizers of the conference. And once again, I would like to thank Karthikeyan for inviting me for this talk. And thank you so much.